There we go. Okay, recording. Yes. So yeah, thank you again, everyone, for coming. Happy to share with you some new discoveries that we've made with the MMS mission. It's of course an impossible feat to summarize a decade of the progress that's been made with MMS, but I will certainly hit some highlights along the way and do my best for that after I accept the recording that's happening. And you notice here the screen for in person is cut off a little bit. This is the year 202. But yeah, it's okay. 2024. So, and then the title here, Electrons Can Smile, even though they're negative, believe it or not. Let's see if this is true. So actually a little bit of a story for the title. So this past AGU, I was told very definitively by Andre Grunov, came to my AGU presentation, and he said very seriously, Jason, electrons cannot smile, they're negative. But, au contraire, we have some, so you can think by the end of the talk if I've convinced you in fact of that. So again, the other interesting coincidence, perhaps, is that maybe not coincidence, but you could say I've been waiting 9 years to the date to give this talk, because it is 9 years to the date of the launch of the MMS spacecraft. So it's a very exciting time, and in fact, you can debate whether it was on the 12th in Easter time or on the 13th in Universal time. But anyhow, it's been 9 years here, and so this mission of MMS, right? There's a little bit of background of what is the MMS mission for those who might be new to that and new to this field. So in a word, there's a lot of things you can do with MMS that we're going for, but the main baseline science goal is to determine the microphysics and the kinetic processes that basically fuel magnetic reconnection, right? So that begs the question, what is reconnection? And I'll get into some of that as we go. But MMS is specifically designed with that goal in mind. It's a 4-spacecraft mission, and the resolution on MMS is unprecedented. So you've got 30 millisecond resolution for electron distribution functions, and you have 4 different spacecraft trying to surround this diffusion region of reconnection. So there's really quite a lot that you can do here. This is actually a photo courtesy of John Macri of the launch, for those who are able to see it in person. So I'm going to get into more of all that in a second, but I have to start with some nostalgia, of course, too. So I did mention a decade of discovery. So I dug through my old slides here. It was in fact a decade since I gave the last seminar here at UNH. So smoking gun observables is the theme of my dissertation work. That title actually came courtesy of Roy Torbert, one of our group meetings. He came in and asked us that very question, what constitutes smoking gun evidence of reconnection, right? So we were all thinking about that as a group, and that made it into my dissertation work. A photo here of Mom and I and some other friends and family who came to see the presentations. So I had to throw that in there as well. And also, before I get going, I would like to dedicate this talk to some very important influences in my physics career from here at UNH, Professor James Harper and Professor Carson Pohl. Unfortunately, no longer with us, been very much missed, but I've been very much inspired by them and many of the scientists here, but I especially wanted to dedicate this talk to them and have a couple of quotes from Jim Harper, in fact. He says, if you find yourself stuck, think of the most important part of the word research. You must search and search and search again. I find that to be very true, in fact, and for anybody feeling stuck, take that to heart. Another quote that Jim had shared with me at the time: the more at peace we can be with uncertainty, the more at peace we can be. So I think those are some profound words of encouragement, and both Jim and Carson really encouraged me. I met Carson actually, it was my first taste of freshman physics back here in studio physics back in the day, and then also had him in graduate school. One of my favorite physics classes actually was our complex analysis piece and mathematical methods in grad school as well. And the theme here that I wanted to emphasize is that we all need encouragement, and encouragement goes quite a ways. And so I showed this little newspaper clip that I found off the side. Here's a zoom-in view. This was just one day in Demerit in my mailbox. I walked in and found this here, and Jim had left this to me. We had actually started the UNH Chess Club, some colleagues of mine, and he saw this article that made it to the paper. And he just wrote, Jason, great job teaching chess with your friends, keep it going. So I think, encouragement can be just as simple as that. I always remember to this day, I still have the newspaper clipping. And actually, I'm still playing chess with my friends.
Is that you?
What's that? No, this is one of my friends. This is Ben Johnson. So,
okay.
Yeah, he was one of my freshman year colleagues. So we started the club together. We played at the elementary school, Mohammed Elementary. So we had a good time, teaching chess and sharing that with the community. And I'm still doing that, following Jim's advice, keep it going. So actually about 10 days from now, I'm going to be headed to Africa, to Uganda and Kenya to share chess and continue teaching chess with the world. And some friends of mine, I'm in this little thumbnail there, and the hexagonal one, if you can see it. And if you haven't seen the movie, Queen of Katwe, it's a Disney film, true story, a very inspiring story of Fiona Mutesi and her teacher, Robert Katande, who I've had the pleasure of meeting in person, and we'll get to help them out in 10 days as well. So yeah, this verse here, encourage one another daily as long as it's called today. I think it's always going to be called today for quite a long time. So let's remember to do that, and I hope that you're encouraged by my talk here as well. Jumping back to physics too, I have to throw this in. So at the equator, I don't know if anybody has seen these demonstrations, but I should say demonstrations of the Coriolis effect. They claim that if you're at the equator, right on the equator, if you pour water in this bowl, it's not going to swirl at all. And if you go to the right to the equator, you're going to get your counterclockwise flow. And if you go to the left, you get the clockwise flow, which of course they failed to recognize that at the equator, the effect doesn't happen. But, this is something I don't know how this is a tourist attraction, so I don't know how they'll feel about me correcting their physics, but we'll see. That's one. So I'll let you know how that goes when I get back. All right, so without further ado, back to the magnetosphere and to MMS. This is one of my favorite artist renditions of the magnetospheric environment surrounding Earth. So we have this supersonic solar wind flow that bombards our planet, bombards the magnetic field, and sets up this shock wave where you have the bow shock on the front. And then you have this inner magnetopause boundary in the inner region between the yellow and blue regions. And so MMS was specifically designed to actually measure two regions, both the day side and the tail region, and to catch reconnection happening on these places. But so in this talk, I'm just going to focus on the day side here. And so you can imagine MMS is basically like a microscope, really zooming in to very, very small scales, small in terms of plasma scales in this case. And so that's why I think the acronym of MMS is kind of easy to remember if you think of it as the magnetospheric microscope in this sense. And you can use it both as kind of a telescope, but in this case, we'll be zooming into the smallest scales. And in fact, MMS has set the Guinness Book of World Records, actually two of them, one of which is for the closest flying formation, closest spacecraft flying formation. They've gotten to around 6 or 7 kilometers between the inner particle, or between the inner spacecraft separations, which is remarkable. So in the order of this, graphic, if you kind of imagine a rough scale, about 10 RE for the full, size of this boundary here, that's on the order of 60,000 kilometers. And the separation of the spacecraft is 6 kilometers. So you can imagine zooming in about 10,000 times into these very, very small boundary layers to actually catch reconnection right at its source and at its heart. So that's the goal here of MMS and what we're trying to do to dig through reconnection. And just give you a sense of what the data looks like without going into all the detail here. A quick 2-minute view of data on the left and a 2-second zoom in now here on the right. And so let me point out here on the left as well, these are the types of very thin electron scale current layers that we're able to measure with MMS. In this little window, it might be a little hard to see from distance, but there's a sharp spike in the current density. And that jumps right out here. And when you zoom into that view, those are the types of structures you want to find in these EDRs. In this case, it actually wasn't a diffusion region. We're probably off on some edge of the reconnection site. And so, with that microscopic view, you're seeing things that you haven't seen before, and it's hard to even orient yourself in the data. But even then, just to show you an example of the resolution of MMS on the right, even just 2 seconds of data is rich with wiggles and little structures to kind of zoom in and see. And in particular here, just starting from top to bottom, some of the basic plasma parameters we'd like to check: magnetic field structure, density, plasma density. And in particular at the bottom, we're interested in seeing things like gradients in these plasma quantities. So gradients in the density, gradients in the pressure and temperature. And that's actually what we're showing. We can resolve that now with the FORCE spacecraft for the first time at the electron spatial scale. So I'm going to kind of come back to these zoom-ins in a minute, but that's just a taste of what we can see with the MMS data. And before that too, I want to also just kind of give you a sense now of what we're going to be zooming into. So my field, my kind of focus is to look at distribution functions. And that's really taking a kinetic view of plasma, right? So you can kind of think of two different ways of analyzing the plasma. You can think maybe at a fluid level, where you're imagining quantities that we're more familiar with, like wind and density and temperature. But you can also zoom into the kinetic scales, the smallest scales of your plasma. So then we're actually tracking individual particle motions and trying to understand kinetically what's actually going on. So one of my favorite kind of analogies of this is I brought the in-person example, tested it before, so it should still work. There's this little toy called the Galton board, and it's all these like thousands of little beads. They kind of trickle down through these pegs, and even though there's all this kind of chaotic, motion between all the beads, you can never predict with any accuracy where one particular bead would end up. But you can almost always predict the final state of this kind of curve, or the distribution of these beads, if you will. So as I go through the talk, I want you to think of the MMS measurements I show as kind of like a Galton board type effect that we're seeing in space. Now, the other difference too, kind of going back historically, right? A lot of these ideas, Galton was actually contemporary with Boltzmann, so the Boltzmann equation and Boltzmann constant. And so then they're thinking of much more idealized collisional systems, where you actually have collisions between all these little inner particles, kind of shown by this animation on the right. And that really collapses your distribution to, again, similar to the Galton board, one shape every time, and that shape is a Maxwellian distribution. So when you talk about something like the temperature, you read the temperature on a thermometer, what does that mean? That's basically the width. It would correspond geometrically to the width of this distribution of all the particle speeds and velocities. So it's a really neat geometric connection to kind of the physical notion of what we think of as temperature and average kinetic energy, right? So that's all fine and good, but this of course is for an idealized system where you have these collisions that are kind of like the beads, causing their particles to kind of decide in a binary sense which way to go. It really collapses the distribution very rapidly to a Maxwellian. Could fast forward now to Vlasov and Landau and some of the others who first had some of these early reconnection measurements, Giovanelli with some of the first neutral point measurements. So now you get really interesting things in a plasma, in particular in a collisionless regime, in a collisionless plasma. So now you don't have that same constraint on the distributions, and you can get very exotic non-Maxwellian structures that show up in the velocity space. You can kind of have coexisting populations of particles with higher energy and lower energy, and they're not necessarily going to have to kind of dissipate some of that energy and collapse the distribution to a Maxwellian. There are a lot more solutions there, and especially a lot more exotic behaviors as well. For instance, Landau damping, a very hot topic as of late, where you actually get damping of plasma waves without that underlying collisional mechanism. So that's very much an open question as to how that works, and MMS has actually taken some steps to observe this. And I'm going to circle back to this toward the end as well. But so one of the ideas and motivations here and some of the projects I'm involved in does involve, in fact, studying this mechanism of Landau damping. And unfortunately, it's a lot of our global scale models can't necessarily capture this type of physics. We can get it pretty well at the fluid level, but when it comes down to the kinetic scales, it's just not going to be able to capture it. So the recent effort here, Jan Gondarelli at Goddard from my former institution, they have a project here called, the great acronym, I have to say, MARBLE, Magnetosphere Aurora Reconnection Boundary Layer Explorer. So this is still in the works. It's going to be an open source model. It's one of the first times they're actually adding in some of these kinetic effects to try and get the type of physics you need to see Landau damping in a global sense. This is also just showing too, even in the mathematical community, this is a recent Fields Medal that was awarded to Cedric Bellamy for work again on analytical methods studying nonlinear Landau damping mechanisms and these types of things. So it's big news, not just in the physics community, but plasma physics gives you a great kind of tool and a great test bed to even test for these things and study Landau damping in action. And so, yeah, so again, sort of setting the stage here, since I look at distributions all day long, it's easy for me to take for granted the plots I'm going to show you. But if you just think back to, again, the basics of physics, right? If we just zoom out as far as we can go here, what are the basic questions you can ask about a measurement? Say you see a time series in some probe that you built, and you're wondering, okay, what does this mean? How do I interpret this? So the basic things you can ask are about time, space, and speed, right? Things like how long did it take? How big is this thing as it moves past me? And how fast was it going? Or which direction it was going and all that, if you include some velocity. And so those same questions, keep those in mind as I show you these next types of plots. And in fact, so when I talk about the distribution function, and I'm talking about, I showed you some of Vlasov's early work here. When we talk about something like the Vlasov equation and this collisionless, collisionless regime that we're studying at a kinetic level, it's the same type of questions. It's just embedded in a bit more mathematical complexity. So the equation at the top is the Vlasov equation, of course, as many of you might recognize. And each term, as intimidating as it might look to a non-specialist, the first term is just asking questions about time. How does this distribution change in time? The second term is asking how it changes in space. And the third term, hardest to write down, most complicated conceptually, but it's basically asking how these particles are changing in speed as you move in energy from different places in the distribution. All right, so all those basic questions are still there under the hood. We're just now asking specifically, how does this apply to a distribution function? Despite all the complexity of the distribution and all the different measurement spaces, we're typically used to think of that kind of animation of particles in position space, X, Y, Z. The other complexity here conceptually, and why we haven't had many observations in this case, is that the Vlasov equation and Boltzmann's formalism takes place in a 7-dimensional phase space, and sometimes even higher dimensions than this. But if you think of this kind of single particle distribution, you have 7 different dimensions to keep track of, right? Your original position, X, Y, and Z, and now also 3 velocity components, Vx, Vy, and Vz. All right, so now with MMS, we're trying to basically understand that and study the distributions at this basic way. But we actually can do that. We have all the machinery with MMS to do it. In particular, the 4 spacecraft enable the spatial gradient term for the first time. So that is really a novel piece here. And just to further motivate conceptually, what is this Vlasov equation telling you, right? Well, if going back actually to a question John Meredith asked me at the time, I think she had said, how would you explain angular momentum to a 6-year-old? So in the same way, I'm trying here to explain the last sub-equation to, to somebody who's has no idea about the kinetic equations here. But geometrically, what it basically is telling you is it's a continuity equation. Okay, it's a continuity equation in phase space. And it's saying that, that right-hand side of the equation is equal to 0. You don't have any particle collisions. You don't have any sources or sinks of plasma. There's no ionization. There's no recombination. There's no losses like you get in the ionosphere. It's particularly in a region where you don't have any sources and sinks of the plasma. And as a result, you would see this relationship between the three terms on the left. And what MMS is doing, MMS has the capability to very rapidly measure individual chunks of this phase space and actually counting particles. So you're literally just counting these little beads, if you will. These are kind of just an example phase space here. And this, of course, is in a one-dimensional view. So if you tried to visualize 7 dimensions, that would be very difficult. So instead, this is just a one-dimensional kind of example of this. And the horizontal axis here is your x variable, or your position space. And the vertical axis is your velocity coordinate. So you kind of imagine the further you go up and down on the plot here, the faster the particles are moving. And as you move left and right, these kind of blobs are swirling past your spacecraft. And so again, here, you might also start to get intuition of what I'm about to show you, is that in this situation where you have a continuity equation, you're not losing particles anywhere, you would expect that as particles move in and out of this bin, this little measurement bin from the sides, highlighted in green, they have to come from somewhere or go somewhere as a result. So they have to come out the top and bottom somewhere, or vice versa. If they come in and out top and bottom, they have to go in and out on the sides. And that is if you have a constant, a steady state situation. If you can imagine that the number of particles are kind of the same here, then you might expect some correspondence between these two terms. So with that intuition motivated, that's going to make a little bit more sense as we come along here. So I want to first, before I jump to the results, show also how MMS is actually able to take these measurements. It's very remarkable. So featured on the bottom left here, the DES instruments, dual electron spectrometer units. There are actually 4 of these dual units per spacecraft, and there are 4 spacecraft. And so you actually get 32 of these detectors to make these types of measurements. And you're going now from position space. We can't really track all the different particles in space, but we can measure their energies and their velocities when they come to these detectors. And what you get in the bottom right is an example of one of these distribution functions. And it's kind of full glory here. And just to give you again a sense of scale, we're measuring a fully 3-dimensional distribution function for both electrons and ions every 30 milliseconds for electrons and 150 milliseconds for the ions, faster than ever before. And also to give you a sense of the typical speeds of these particles in the velocity axes, they're in the order of anywhere from 5 to 10,000 kilometers per second, is a typical thermal speed that we'd be measuring in these regions. And one other thing to note, you might have noticed this already for those who are familiar with these types of distributions, this particular distribution is actually taken from that little spike that I showed before in the little current layer. And it is anything but Maxwellian, right? It is not just circular. If it was circular and uniform, you'd say, okay, that's more of a typical Maxwellian shape that we would have expected. This is not that. You might notice there's an extra blob of particles on the right-hand side. And in fact, this is shown in the plane perpendicular to the magnetic field, which is particularly important for plasmas. It also means that this distribution is non-gyrotropic as well. So there's no longer symmetry in this plane. So it's a very interesting distribution to study, and we see these types of crescent-shaped distributions all over the place. But all that detail that I'm showing you is just from one MMS spacecraft. And the point is, to get to these terms in the last sub-equation, we have to look at changes in here. So changes in time, changes in velocity, changes in space. And we happen to have 4 spacecraft. So we can do exactly that. If we thought we didn't have enough information in one distribution, we can actually now look at all 4 of them and start to ask questions like, how does the distribution change from one bin to the next as I go from MMS 1 to MMS 4, for example. And doing so, this is kind of our novel methodology here, we actually get a distribution plot that looks something like this. So this is, sort of unexpected, and it's a different color bar than we're used to seeing. So it's no longer now kind of measuring the number of particles in the bin per se, but it's actually measuring something much more dynamic. Right, this is now a question. This is a spatial gradient, in fact, in one particular direction, and it's answering the question: how does the distribution change as I move into the current layer? That take one step toward those more energetic particles, right? So at first, when we ran the method here to actually compute this, it's a 4 spacecraft gradient technique, similar to what's used, for instance, in the kilometer method to estimate the current density for magnetic fields. But now we're just running that technique on every pixel in velocity space, right? And MMS and DES in particular measures a lot of pixels in velocity space, up on the order of anywhere from 10 to 15,000 pixels. So it takes a while to even compute the gradient in this fashion. But doing so, you get a brand new type of measurement, and it's telling you a lot about what the plasma is doing, not just at one point, but as you spatially move around in the plasma from one space to the next. So to even motivate this as well, right, if you imagine that crescent-shaped population was kind of carrying the current in this case, this is telling you as you step into the current layer, of course, you're going to see more current-carrying particles, and hence the color is red. There's more particles as you take that step in that direction, and then vice versa. You're seeing fewer lower energy particles as well, since the distribution effectively is shifted in that direction as well. So each of these pixels and the colors are telling you something meaningful. Of course, not all of them. As you get closer to the instrument threshold, the photoelectron contamination kicks in. So there's a certain kind of sweet spot of a range where these measurements are valid. And we actually went into quite a bit of detail to check this. And here, as one more interesting puzzle here, so now you notice this spatial gradient term that I showed is just the actual gradient part. It's just a spatial sense. As I take a step, how does the distribution change? And now as you dot that with the velocity component v, this is now the term in the last equation, v dot rad f. And it's important to note too, this little v is not the bulk velocity of the plasma, but it's the actual kinetic fluid parcel in the space velocity, right? So you're taking the velocity component of each pixel and dotting it with this gradient. And you get a somewhat surprising result, this interesting quadrupolar feature. So what does that even mean? Well, it actually makes sense if you think about it from an electron perspective, right? So half of your velocity space with this v per 2 component greater than 0 is moving, as I said, toward the current layer. So you'd see the red and the blue feature like I just described, but the other half of your distribution is moving away from the current layer. So then you're going to see the opposite of that. You're actually going to see fewer current carrying particles in that direction than you would in this region as well. So you get that really kind of interesting quadrupolar feature just for this kind of quintessential distribution you'd see in these types of crescent layers. And it's just, it made it scratch your head for a while to see if this is even valid. So, yeah, good question. Chris?
So would this be like the meandering orbits, one going one way and one going the other way? Is that like separated out there?
You can think of it like that, yep. So the crescent of the electrons, some of the particles, like the reason you see a crescent, for instance, is that they're not completing that full gyration. Otherwise, you'd see more like donut type distributions, which actually we're sitting in front of donuts, so we have a great example of this. So yeah, instead of the full donut, you kind of a ring-shaped distribution, you would actually get these types of partial orbits. And so yeah, in this case, it's a little bit non-intuitive why you'd see the quadrupole. It's not really expected at first to sort of understand that. But when you do think of it as half your distribution is kind of moving in one direction, you're kind of dotting it with the velocity of those particles. So half of them have a positive v, and the other half have a lower v in this particular gradient direction. So yeah, it could be related to some of the meandering. And actually, this is going to get to the end of the talk. We do actually look right at the heart of the EDR with this method to see what we, see with MMS in this case. So now I'll show this as well, just again, go back to the idea of how do we know that this is even kind of a reasonable thing to be doing. So we actually have a somewhat recent paper in Nature Physics kind of illustrating this and just coming up with a first principles model of what you might expect to see in the velocity space. And lo and behold, we do in fact get these types of quadrupolar features popping up. So that was really reassuring. We did some work to try and then understand intuitively how you'd link that back to the fluid picture that we think of. And here's an example of lots of these types of red-blue signatures. And the kind of takeaway from this is that each type of fluid gradient that you might expect, whether it's a density gradient, or whether it's a bulk velocity gradient, or a temperature gradient, each of them has a distinct signature in this kind of gradient space of the distribution, if you will. And so that, donuts, for example, are bipolar features. A symmetric quadrupolar feature in the v dot rad f term would be related to the bulk velocity gradient, and so on. And so the one we saw was the one on the bottom right, where it's actually kind of this skewed crescent. It's a skewed quadrupolar shape, and it's representative of a combination of these gradients occurring at the same time. So it's really kind of building up a new sort of like set of basis functions, if you will, the types of structures you might see. These also, to me, happen to look like quantum orbitals as well, but that's talking on the scale of angstroms as opposed to the scale of kilometers here. But it's just interesting to think of them almost by these distributions. And a little bit more context, right? So this is just a single time right at the peak of the current layer, like I mentioned before. There's the kind of crescent-shaped red-blue feature in the gradient, and then the v dot red f term with this skewed quadrupolar term. And we did some work here as well in our 2019 paper to understand conceptually, what these structures are actually telling us. There's an integral equation that I just hit over here, which kind of shows a nice correspondence between these types of gradient terms, the v dot red f term, and in particular, the fluid variable of the pressure divergence, the electron pressure divergence, this div PE term. And that's very important for studies of reconnection, where often this kind of electron pressure gradient is believed to be responsible for the reconnection electric field. And it's kind of a little bit of the magic, if you will, of reconnection seems to be just thrown into this term. So to actually see this now in velocity space for the first time in more detail is very interesting. And intuitively, you can kind of think to yourself, all right, it's the integration over this last row of distributions. We're getting so much more detail in velocity space, but adding up all those red and blue regions and kind of seeing their competition between these different spaces or different particle regions is actually giving you the net pressure divergence, right? It's the integral of that term is what we usually plot when we check something like a pressure gradient. So it's very interesting to see, how these types of tools could work to understand the reconnection and really dissect pressure divergences in a way that we haven't been able to do before. All right, so this contrast as well, you can see the top row is just the distribution function, which by itself has plenty of information in it. But now we're seeing again this dynamic measure in velocity space, telling you a lot about how that distribution is changing from one spacecraft to the next. Yeah, so now this is all just the v dot grad f term, right? There are two others in the Vlasov equation that I haven't touched on yet, but I'm about to in a minute. But just to give you a sense also, these are also slices that I've been showing you. They're not reduced distributions, but MMS can just take slices in the velocity space. And this next animation here is courtesy of James Webster, where you can kind of get a sense of, I'll show the whole movie, but you can get a sense of just this sort of 3D nature of these structures. Your original distribution is off to the left. We've kind of interpolated here to a Cartesian grid. And you can imagine taking these different slices of the velocity space to really understand what the full 3D structure of this thing looks like. There's kind of that crescent distribution that was sitting there before, the quadrupolar thing that we saw over in the velocity space as well. And you could check the other planes as well. So even one distribution by itself would have a lot of information to just understand and dig into. But we certainly have the capability to do that with MMS. So if I just speed through here, you can see some of these different slices. All right, here's the last orientation here as well. All right, so that gives you a sense of some of the full glory of the measurements that we're taking in vivid detail, zooming into this kinetic perspective here. And now I can start to build up this figure with some data. All right, so we just saw this. This is now the spatial gradient term. If we kind of go from left to right, where we're taking 4 different distribution functions from MMS. We're able to get out that v dot grad f term for the first time, and we kind of have our model as to what we think that means in terms of moving into and out of current layer for this case. Now let's look at another one. All right, so this one's actually a little bit simpler conceptually, the time derivative term. Now we don't even need the 4 spacecraft. Now we can say, let's take a single spacecraft and check in time. I have a distribution at one time, 30 milliseconds later, I measure another distribution, FV of T1, FV of T2, and let's take their difference and see what they look like. Okay, so that's what we show in this next plot here, this df/dt term. You might notice if you squint, the colors are almost inverted from the spatial gradient. Instead of a red crescent and a blue core, now you have a blue crescent and a red core. And that also makes sense if we think about it. First, it was puzzling to see why are we getting into the same thing here, but roughly speaking, these structures are kind of in steady state as they move very fast past the spacecraft. And so you could imagine that effectively the structure is sort of frozen in time as it moves. So any spatial variation that you're seeing with MMS is then very much going to be like a temporal variation you're seeing as well. So the change on one spacecraft is effectively measuring the spatial difference that you're seeing as well. And so that would sort of explains this first term, why you might have expected this. And then furthermore, you can use that term, as we showed in our paper, to then basically get the same thing out from the spatial gradient term.
Jason, to clarify, when you take that df/dt term, that you have taken out the convective change, is that correct?
Well, actually, we're just in the spacecraft frame at this point, so just the MMS frame. So yeah, I just did the simplest thing possible, where I just said, I have a time measurement at T1 in my time series, I measure the distribution again, and I just take their difference. So all the calculations are done in the MMS tetrahedron frame. So we didn't necessarily have to do any shifting of the structure or anything. And even to that point as well, the other thing is that these electrons, these velocity axes, are in the order of 10,000 kilometers per second for a thermal speed. So any convective motion as well is about 2 orders of magnitude smaller than that as well. So it's a very slight shift in the velocity space at this point. So yeah, we didn't have to necessarily worry about that for these 2 terms.
Normally, as I understand that term, I would have to take the convective change first.
Right, like if we applied it, say, to the fluid quantities, like dn, like a density gradient, for example, right? Yeah, if you wanted to kind of shift it and then actually get kind of the same quantity out, you would need to be able to do that shift as well.
Okay.
In this case, if you're just in the same just the MMS spacecraft frame, you can still, I think, evaluate in either frame. In fact, if we were to go back to the Vlasov equation and we shifted it, if we shifted the frame, and you can actually check to see these terms that are frame dependent or frame independent, the first 2 terms of the Vlasov equation together will be frame independent, because if you change your df/dt, then you get the convective piece that you have to add in. And then if you change your v dot grad f, that v is also going to be shifted by the same velocity shift. So yeah, we took some scratching of the head to make sure that, these terms are actually doing what we think they're doing. But you're right, like this convective piece is something that, at first was very puzzling. Actually, speaking of puzzles, so the other thing you might notice if you're looking very closely, the color bar here for this dfdt term is on the order of, in these appropriate units, 10 to the minus 26. But the actual spatial gradients that we're seeing is 10 to the minus 24. So 2 orders of magnitude larger than this entire dfdt term. Right, so that again goes back to thinking, okay, at first in our earlier work, we just neglected this term and said it's much smaller, than the other spatial gradients here. But it turns out there's actually a subtlety in this velocity space that you can actually multiply by the appropriate velocity space coordinate, as we show in the upper right. And you're basically just now taking temporal measurements only, measurements from these two different distributions, measured at 2 different times, and comparing it to a completely different type of measurement where you're taking 4 spatially separated points and generating this v dot grad f term. And you can see the correspondence, it's very close. It's very close to the same. And the reason it's so close is because the steady state assumption is reasonably, works reasonably well for this particular event. Now, some events that may not be the case, in this case it is, and so we expect to kind of see this correspondence. And I'm going to show later in the talk as well, it actually motivates a very interesting kind of checks and balances approach to these distributions to decide, which one is more resolved for your event of interest. But before I, dawdle too long, let me at least show you the next one. This is the hardest one to compute as well. But as you might have expected by now, you kind of see the same thing in 2 different terms. And lo and behold, for the third term, f dot grad vf, we do also get the same type of quadripolar feature. But you might also notice too, the color bars are inverted. Right, so as we showed before in that kind of conceptual animation, where the particles kind of coming in the sides have to go in and out from the top and bottom, there is a minus sign that you would have to have in the Blasov equation to see between these 2 spatial gradient terms. So it's a very interesting result here, the fact that MMS can measure sort of the same thing, if you will, but 3 distinctly different ways. 2 different points in time for a time derivative, 4 different points to get a linear spatial gradient term, and then now, not even taking 2 different points in time or 4 different points in space, taking a single distribution function, this is the one I showed before with the crescent distribution, and just evaluating the velocity space gradient of each of those pixels, because we have a lot of pixels, right? So you can say, as I go from one pixel to the next, how is that phase space density changing? And evaluating the gradient that way, you get a corresponding result. So it's really interesting to see. You might have then zoom out and think, well, okay, why does this matter? We know the Blasov equation is probably true in these regions. Is this unexpected? But there's many different kind of unexpected pieces that kind of come with this, which I'll explain in a minute. But a lot of this is just interesting that you can kind of take the same see the same type of physics from completely different ways of measuring it. And that was just for one event. This is another event that I mentioned as well, just to give you kind of a sense of showing all 3 of these terms at different times as we go through this particular current layer as well. You might see the familiar kind of quadripolar pieces that we saw before in the spatial gradient term and the temporal derivative terms. And you can now compare just with 2 different spacecraft, like with 2 different and single spacecraft measurements, that is, you don't necessarily have to rely on this 4 spacecraft measurement for this type of comparison I'm going to show you. What you can actually do now is say, all right, maybe we don't want to compare apples to oranges. Sometimes when you compute this spatial gradient term, as many of us know, you're kind of averaging over the 4 individual currents that you might measure from each spacecraft, and there's a time to do that and then a time not to do that. But you can also then say, well, this is working pretty well from our temporal gradient term. We could compare that 1-to-1 with the velocity space gradient term and then actually evaluate the balance, or attempt to evaluate the balance of the Blasov equation terms in velocity space. So that's what we're attempting to do here. And the last row of these distributions shows this attempted balance. And again, taking the single spacecraft measurement of the spatial gradient term to kind of compare it with that third term as well. So you can certainly see the qualitative agreement in rows D and E. And then with the balance, you then start to have to ask some questions here. So is it even a physical measurement? But
Sorry, quick subscript, the perp 1 and 2, what do 1 and 2 mean?
Oh, for like over here.
Yeah.
Perp 1. Yes, good point. So when I showed that distribution before with the crescent space, so perp 1 is roughly the E cross B direction. We kind of just pick 2 different perpendicular directions to the magnetic field. So you can think of perp 1 as roughly your E cross B direction, where the kind of the overall drift motion of the particles. That's why the electrons were like shifted in that E cross B direction. They try to stay as frozen as possible. And then perp 2 is roughly speaking along the E direction, like along the electric field, or basically along the density gradient direction. So as you like step into the layer, that's why actually all of these perp 2 structures are like symmetric along perp 2, because you're kind of like stepping into the layer that way. So this half the particles are moving toward the layer, and this half are moving away from the layer. So yeah, so just two different perpendicular directions we choose to plot the distributions. And I'll say here, so this is not necessarily physically showing you what the deviation from the lasso equation is doing as much as it is showing the limitation of our instrumentation. But to be able to see it in velocity space for the first time is particularly important. You can then imagine, for instance, other missions, beyond MMS, like MMS wasn't necessarily designed to measure the intricacies of phase space in this detail. It was a bit of a serendipity where we just ran our gradient code in velocity space and, to see what would happen. So the fact that it works as well as it does, certainly at the qualitative level, begs the question of, what could you learn about other environments, for instance, where you don't necessarily just assume collisionlessness. You could actually quantify the degree to which these plasmas are or are not collisionless. So this kind of gets it a way to do that here when you do this detailed analysis of all these types of terms. And like I mentioned before as well, this kind of remarkableness of seeing the same thing but measured from entirely different ways, that really enables a type of checks and balances approach in my mind when you make these types of measurements. We typically just jump straight to the moments level and say, what is my electron scale pressure divergence? And does it balance the reconnection electric field? But how do you know what that measurement actually was, right? It started in velocity space effectively. And there is an equivalence, right? You could, of course, take the moment and get your pressure tensor terms and then take their gradient and get your pressure tensor derivatives. Or you could take the derivative in velocity space first before integrating. And it kind of gives you this view of what your velocity space looks like before doing that. You wouldn't have necessarily seen these, expected to see these structures or even had an intuition in velocity space for what you'd see. But the fact that you do have these coherent structures in three distinct ways of measuring it is particularly interesting here. And that'll be very interesting too as we go forward and jump ahead. So I want to make sure now I have some time to cover these last bits. So this was, of course, the MMS side. And we did some work on the theory side as well. We looked at exact Maxwell solutions of these in a 1D case and saw some correspondence with the crescents. But I want to jump now to a fully kinetic simulation. This is a particle and cell simulation in 2D or 2.5D, as they like to say. So here, of course, to orient you, we do see, in fact, a crescent distribution that we'd see right at the X line. This is kind of showing you now the color quantity of the electron pressure divergence term. And right in the middle, you do see this crescent, as expected. And this is the part which motivated the title of this talk. What would you expect to see right at the X line, for this distribution if we plotted these gradient terms, the gradient of F and now the V dot grad F term in the last equation, right? So surprise, surprise, we get a very intricate structure in velocity space. And you can't make this stuff up. Like I didn't just, do this in PowerPoint, that's just there. It really did make me smile at first. It is kind of like a tilted smile, it's a little, maybe a creepy clown shaped thing, but anyway. And then it makes you wonder, okay, well, what does that even mean? Is you have to go back and kind of understand. So I'm just going to take you through a slice of the simulation to show you what some of these like inducts you can actually see here. So these are what some of the gradient structures look like in the simulation as you fly through. You can imagine this is a virtual spacecraft flying through the box. And right here now, we've hit that kind of smile region right at the heart of the X line in between these bipolar pressure gradient signals. And then now we kind of exit out. So if I do that again, just in rewind rather quickly, you can start to see some of the features we saw before. There's this kind of bipolar shape thing in the gradient term, quadrupolar pieces that we saw in the V dot grad F term when we were just outside the EDR. But presumably, according to the PIC simulation, if you get right into the heart of the EDR, you're going to see something very highly structured and perhaps even a smile type shape. And what is it telling you again? So this is a spatial gradient. So it's saying, as you take a step up through this layer, these regions of velocity space are going to see fewer electrons. Whereas this inner part of the crescent is going to see an intensification of the counts right in the inside part of the crescent. So as I flip through the rest of the layer, you can now look at the distribution and see that that actually happens. The gyrophase extent of this crescent population is going to shrink, but then the intensity of the crescent is almost going to get concentrated right as you get toward the outside part of the layer. So you might have seen that before, but here you can see the shrinking of the distribution and then the intensification. You now have a much thinner and gyrophase extent, a much smaller kind of crescent shape, but then also a much more intense crescent at this point. And then, of course, as you keep going out, you eventually don't see the crescent at all. And so it just vanishes away. So that's kind of how you can interpret some of these very complicated structures in the velocity space. So a quick summary of some of those different terms from the simulation, and the smile distribution that appears there is quite remarkable. And then we took this and then thought, okay, it's one thing to see quadrupolar features and crescent-shaped things with MMS, but surely you wouldn't be able to measure in that much detail to get something like a smile out of MMS, right? So we're starting to look now at work in progress, but looking back at the electron diffusion regions that were observed by MMS. This is, of course, some of the things to highlight of 9 years from now, we have a lot of different diffusion regions that were caught, the region right at the heart of the X line. This is an example from the first EDR that was reported in baseline from Jim Birch et al. And also we have some tail EDRs as well that Roy presented in the science paper. So here now we're just going to look at this kind of benchmark event that's very interesting to study, that people have studied it quite a bit with MMS. And we're going to do the same game as before. Okay, look at the 4 different distributions that you see at MMS, right at the heart of the EDR, where we believe we're at the EDR. There's kind of this spike in the J.E measure for energy conversion that people like to use to signify this. And what do you think we're going to see now when we take the spatial gradient? Okay, so then here's the other thing I should mention. Yeah, as you know, when you take a gradient, the full gradient actually has 3 different components, right? There's an X component, a Z component, a Y component. There's 3 different slices that you could actually view to see this gradient. So in particular, I looked at all the gradients. I looked at all these, things. I have extra slides if you want to see them. But when we looked at the gradient parallel to the magnetic field, this is what we saw. Interesting. This is MMS data now, not simulation, right? So the gradient in the parallel direction of the electron distribution function has this very similar sort of smile type thing. If you imagine, if you squint and you compare it now to what we saw before in the simulation. Of course, I didn't show you before, but the axes are a little bit flipped, so we need to rotate the simulation one to compare. But you can see then that there is in fact these kind of 2 different regions of kind of the blue electron phase space density change, and there's also that intensification of the crescent on the one side. So the fact that we're seeing that is very interesting. One other wrinkle though, as they say, so this gradient, as I showed you, is when you're moving perpendicular to the field lines. So it actually, we really want to compare apples to apples. We need to look at the parallel gradients in the simulation. And for the sake of time, I'm not going to show all of that, but we actually did it. We checked the parallel gradient, and again, we still see that structure. It turns out we also needed to set the spacing of the different differences, the way the gradient is computed, to be comparable to the MMS separation, which is about 5 dB in this case, 5 electron skin depths. And so when we did that, we're seeing this correspondence. So that's very exciting. I mean, speaking of smoking gun evidence from my earlier work, this to me seems even more like to the next level, and an order of magnitude more evidence that you know exactly where you are in the EDR. And not only that, you know how the plasma, in this case the electrons, is changing spatially as you move around your system at this point. So that's quite interesting. So just setting some of these comparisons side by side. I had mentioned too briefly in the earlier Nature paper, we sort of had a single Maxwellian, a sort of first principles model to understand these terms. Problem with the single Maxwellian is you wouldn't even get any structure in the 3rd term if you just had a simple Maxwellian population. So we added a little bit of complexity to the model and still started seeing some good agreement there. I mentioned this exact Maxwell solution that we studied as well, and we see that correspondence with the crescent. Of course, limitations with the analytical approach here is that you're really only in 1 dimension. It's very difficult to have an analytical solution in 2 or 3 dimensions with that approach. So that's why now we've been starting to look at 2D PIC simulations and comparing with MMS right at the heart of the EDR, like we're seeing here. So it's very exciting to be able to see these types of comparisons. And linking it back to the work that I mentioned earlier, the Marble project, there's certainly limitations in many of these types of global scale models. So far, I've just been showing you, again, that microscopic view in a plasma sense, all these like very fine scale details that you would see. But there are many limits when you start to then zoom out and think, well, how would we get this physics into a global model? And some do very well at some things, but not so well at others. You have different hybrid type codes, for example, where you're actually getting some kinetic ion behavior, but you still usually just neglect all the kinetic electron effects at a kinetic level. But Marble is the first of its kind to really include electron scale kinetic effects, especially in the parallel direction, like we saw with that parallel gradient, which would be relevant to things like Landau damping and hopefully start to see that in a global sense. This work is going to be open source as well, so people should be able to run this and actually be exciting to see what types of predictions you get out of these types of models. So with the last couple of minutes too, I just need to sort of summarize some things and give a highlight of some of the work at UNH that we've been doing as well. So I mentioned some of my project as well, into this global thing with Marble and these studying these lasso terms in great detail. Matt Argel as well has been studying kinetic entropy and related topics with MMS, very exciting work. And there's also a cool visualization and outreach component with 3D visuals that are going on too. So it's neat to be involved in that. And it's, again, I said before, it's impossible to summarize 10 years of the work that's been done with MMS, but some of my favorites, at least in terms of these velocity space structures of distributions. Paul Kasich has a recent sort of coined term of the first law of kinetic theory, if you will, really looking carefully at how these changes in the distribution are taking place, like I mentioned before, changes in density, for instance, changes in temperature, et cetera. And then observations of, or evidence at least, of Landau damping as measured in these velocity space terms. This particular example with Arya Shari and the Chanadel group, they do show, it's different color bar. You can imagine the red-blue features that appear as they try to correlate some of these changes to the distribution with electric and magnetic field fluctuations. And yeah, just lots more that, that can go in and different turbulent studies here that are related to this. And shout out to Christina Pritchard, who recently joined our team as well, just to prove that I'm not the only one who looks at this many Crescent distributions. You know, Chris has looked at even, you know, these papers, you have lots of these questions to study, and you can ask questions about the specific timing of when you see them in each spacecraft and when it exits, and start to infer something about the reconnection structure and all of that. So lots of exciting work you can do with Crescents, in addition to some of what I mentioned. Also, shout out to Kevin Estretti, so actually studying the very detailed orientation of those reference frames that you would need to even observe, for instance, like the normal component or the Z component as you come in and out of the layer, and then linking that to some of his student Stephen's work to study some very clever ways. It's cut off a little bit here, but just some clever ways of backing out the reconnection rate and kind of the aspect ratio of this from locally determined measurements. So very exciting stuff here. Stay tuned for some more papers coming out about that. Also, Jason Beadle as well, and courtesy of Jason's dad, who took this picture of the aurora, you know, again, thinking not just at the micro scale, but then how do we use MMS as kind of a global scale observation as well. And Jason has a very nice work here studying statistically all the different kind of day side passes at that many to close current layer. And then you can obviously start to ask questions about how reconnection then influences things like the inner ionosphere and auroral production as well. So lots of cool stuff to happen here. All right, so just a rapid summary so far of the actual results. MMS definitely gets first place for the first laboratory observation of any kind that I know of, spacecraft or in the lab or otherwise, to be able to actually measure, directly measure all three terms in the electron glass equation. It's particularly remarkable, and we can do this for the ions as well. That's kind of still some future stuff to come. And I mentioned that checks and balances approach. You know, you might say, well, here we have a spatial structure that's actually smaller than the spacecraft separation, and I could use the temporal derivative term to kind of back out the same physics if I want to as well. So there's some really interesting things that lets you do, and certainly relevant for these higher order, you know, moments terms of interest, whether it's the pressure divergence or J dot E is a big one as well for energy conversion. All of these terms, you know, link back to some velocity space perspective. And yeah, as I showed too, comparing to PIC simulations seems to be a promising way to really distinguish where exactly and precisely you are in the EDR when you see such highly structured, you know, smile type things like this. It's very unique to the regions of interest that we're seeing. And I also had mentioned this before as well, kind of the takeaway from this slide is that as we think about future mission concepts as well, even things like helioswarm, for instance, where you have a whole swarm of satellites, you know, it's very interesting to maybe even fly some of this type of instrumentation down the road in a way to be able to quantify for the first time the degree to which plasmas are or are not collisionless. And you can imagine taking that balance term with instruments that were designed to measure phase space, you might actually be able to start having kind of like a flag as to yes or no, or what percentage of collisionality you're seeing just from the spacecraft level without making any assumptions. So that's some exciting future work to come for that as well. And if anyone does want to take a screenshot of some papers here as well, I can circle back to show this. And I would be remiss if I didn't mention the door prizes to those who did come in. I think we already handed out some of the posters. So these are some designs by mom. Shout out to Kathy Shuster. She actually does these hand-drawn illustrations and have them embedded within the eclipse, or a New Hampshire themed eclipse. You can notice the pun as well, the total eclipse. You know, she likes puns. I like puns. And so yeah, the only requirement of taking them is that you have to like her Facebook page. And I do monitor the page, so if you don't like it, I will know. And of course, shout out to Brianna and Tyler as well. Those are Chasing the Eclipse team based here at UNH as well. I'll be excited to see the images that come for that as well. I think that pretty much leads me to the end. I do have a movie of the MMS launch, which you could watch after questions perhaps, but that's basically all I've got for now. And I thank you for your attention. Yeah, question mode.
So you mentioned that there could be, for your paper you have in prep, you looked at the, you know, the famous magnetopause event there. Yeah, and you mentioned that there could be some limitations of the analysis for that event because the spacecraft are so far apart.
Oh yeah, like the 5DE or something, right?
Yeah, I was wondering what's the motivation for using that particular event then, rather than an event where the spacecraft are much closer together?
Yeah, great question. Actually, this is just the first one that I dug into to look at. So basically the goal will be go back to Webster's list of EDRs, for instance, check out a whole bunch of them. One of our students at Maryland, Harsha Guram, has actually been doing this and checking to see what we see for those other events. This was kind of the first one where I knew and felt pretty confident it was an EDR. So many people kind of pick this as a benchmark case. So seeing the smile type structure emerge there seemed like it gave quite a bit of confidence that this seems promising to work on. But you're right, there should be other events where we get more of a distribution of, say, spacecraft spacings with respect to the type scales. So yeah, definitely not limited to just this one event.
Probably already asked you this,
Yeah.
and I forgot. Have you looked at like any of like the electron only reconnection event?
Good question. Have not seen. Yeah, that's another thing to mention of some of the milestones of MMS. Taifan has a paper in 2018 where they actually suggest that there's a new regime of reconnection called electron only reconnection, where the electron physics seems to be decoupled from the ion motion. So instead of your typical 2-scale ion diffusion region and a nested inner electron diffusion region, now they're actually catching these very thin, very turbulent magnetite sheet regions. They're catching seemingly just electron behavior that matches a reconnection profile as opposed to the ion as well. So that would be interesting. With that event in particular, they needed the 7.5 millisecond moments, which then which you can do, you can actually increase the temporal resolution even further if you wanted to, than these DEX measurements. My hesitation with this technique is that there's already some interpolation that happens when you do the 7.5 millisecond moments. So I haven't checked yet and really quantified what our errors would be if we actually try that, but it's a good idea. We should
It's
look.
very short.
Yeah, it's very, right. There's kind of like some different, I forget if they use cubic spline and Amy Rager, of course, to this, but yes, that would be an interesting thing to dig into as well. Yeah. Another question.
Oh, yeah. So, what happens, when there's a guide field, do you still see this, this structure?
Excellent question. I have no idea. Right, so this event.
I have a great event for you.
Okay, yeah. So this one, I should say too, for the Birch EVR, there was a small guide field. I think they said in the order of maybe 5%-ish or less than 10% at least. So I was kind of comparing this to a zero guide field simulation, but that would be another thing to quantify, similar to before where we study the crescents and the triangular shaped things with dependence on guide field and other parameters. That would be a great thing to explore as well.
Well, actually, at least one of them, I forget, because we did look at that one event, where like, at least like the term we read on density gradients, it looks exactly like what you would expect.
Okay, yeah.
It's in that, you did make those plots.
Oh, that's right. We looked at a couple of those, yeah, for like the parallel gradient at least. Yep. Yeah, because again, this is another thing to emphasize in one of my bonus slides. There are different, slices of your velocity space that you can take when you do the gradient. So for instance, it's this one. Oh, yeah. So, yeah. All the extra slides just in case. I notoriously go over time, so I'm actually impressed that it's
No, I mean, too many.
Oh, yeah, all the grids, that's true. But so this one at least gives you a visual of all the different slices that you can take in the velocity space. I know Ever heard you ask the question as well of the convective term and what you might want to subtract, but this gradient gives you, these are different slices of velocity space, V perp 1, V perp 2, I like you test as well, parallel V perp 1, etc. And you can check all these different terms as well for these things. So there's a lot of data that comes out of this gradient term to think about, so. Yeah.
So, Jason, the outside the connection region. So what's the base electron distribution that you get, say, maybe after reconnection or going into reconnection? You mentioned you can't get anywhere with a simple Maxwellian. So what's the most important deviation? Is it from isotropy because you have a magnetic field? Or is it more towards a kappa distribution?
Well, that's a really interesting question. Yeah, actually some of the work that I was doing for the Marble project as well, when they see those types of bipolar signatures and their evidence of Landau damping and things like that, it's a very sophisticated way of taking gradients of the distribution and dotting it with fluctuations. But even just the upstream distribution does have some non-Maxwellian structure. For instance, the straw electron population is sometimes in there, and there would be interesting features that you'd want to kind of dissect and decompose in that regard. I'd say before and after, I wonder if I even have some examples here. This is still like in the EDR, but if I go out to like maybe some of these, for instance. Yeah, you can start to see, so all the way in the upper left, right, before we even hit this crescent region, you start to see some type of more Maxwellian-ish distribution, but whether or not it's kappa or not, I haven't considered. But there is definitely some non-Maxwellian structure in the upstream distribution as well, that I think still needs to be quantified. And it's not just due to the straw. I think it's due to certain things like different regions, whether it's in the magnetosheet sheet, for example, or the magnetospheric side. So that's interesting as well. You would imagine though, if you had whatever that upstream condition was, if you didn't see much change, then your gradient distributions would all be zero and pluses. You wouldn't have much structure. So you really only see these things light up right when you get to those interesting boundary layers. And one spacecraft, for instance, is in the layer, and the spacecraft is just getting to it. So, yeah, so it's an interesting question.
So the, when you're talking about differentiating the reconnected current heaps and the non-reconnected current heaps.
Yeah.
You look at so your first paper, you're looking at like a non-reconnecting current sheet, now I'm looking at the reconnecting. But so you have the particle and cell simulations, but you also have long periods of time of those, so you're looking at like a well-formed reconnection current, like at the time frame you're looking at.
Sure,
But
yeah,
have you looked at it, because you clearly don't have enough distributions to look at.
right, yeah.
You look at the time evolution
Mm-hmm.
of these distributions at what eventually becomes the X line. Have you done that at all, or do you just look at like one time where the signature you expect like really well formed X line?
Yeah, good question. Actually, so for my dissertation work, we looked at the time evolution of just the distributions in the simulation, but we didn't have any of this Vlasov perspective, like kind of the new lens of looking at that. So now that I do have those arrays, I think you were mentioning this earlier, Stephen, but these types of things, for instance, we can make these plots in the simulation now and have the luxury. This corresponds, for instance, to a grid of points here, for example, like really just serving the entire diffusion region. Like you have the luxury of doing that in a simulation. And so then you can start to then say, okay, imagine this grid, but at different times, right? So we should be able to, as long as we have the particle data, we should be able to do it. This again is from an asymmetric reconnection simulation, I should point out. So in the mediative tail, we want to look at symmetric reconnections, so we can certainly compare something as well. Haven't looked at the Vlasov stuff in that frame yet. So, good point. Yeah.
Okay, so by looking at these three terms to great resolution, you can verify velocity equation, we can cross-check. And you mentioned that that's assuming the right side is 0. So when we see something that's not balanced, that means that some other physics going on.
Right.
If that happens, like, obviously it could be due to many things, but is there like first thing you look at, like?
Yeah, something like this one, right, where we see the balance, everything. Yeah, no, that's a great question. I think here, it becomes a little bit of maybe a chicken and egg, right? If you assume Vlasov is right, that the right hand has to be 0, then you could say any deviation from Vlasov in this particular regime has to be instrumental. And on the other hand, though, especially if we started to fly like closer to the ionosphere or in regions where, or even in the magnetosphere for that matter, instead of assuming Vlasov a priori, you can now just look at it from the data and see what you see. I think in this case, any deviations that you see, my assumption is that Vlasov still holds pretty well at this region. So I think these are just limitations of the instruments. In particular, when we measure this third term, it's kind of condensed in this view, but you have 3 different measurements suites in there and 3 different time cadences for the electric field, the magnetic field, and then the electron velocities as well, plus taking gradients of the distribution. So there's plenty of sources of error as you get those, as you try to compute these terms. So I think the qualitative comparison is robust, but the actual, deviation here, as you said, if we really trusted the instruments, then you can interpret this as some other physics that's happening in there in velocity space. But that would be kind of a new thing. So that's something to do.
One more quick question.
Sure. Yeah.
What's your favorite MMS spacecraft?
On this slide. MS3, I picked that only because I've used that one for this figure. Some of the other spacecraft have started to lose some of their spectrometers, but if I had to pick one, which is difficult to do, but I'll say MS3. So how does that compare with yours? Your favorite? After this.
I love them equally.
So Jason, you mentioned taking this potentially to look after non-Vlasov effects like effects of collisionality. So if you want to do that, I think then you may have to go in and really come up with a rigorous error determination on that last line.
Yes.
To say, okay, is this really a significant deviation or just an artifact of putting together all these measurements?
Yeah, absolutely,
It's like
absolutely.
Really well characterized instrument response.
Yeah, well, actually, and speaking of that, so Dan Gershman, who worked with me very extensively to kind of get this technique up and running, courtesy to Dan and Barbara Giles as well. Dan has a lot of interesting work on the uncertainties in the FBI measurements. And so what we actually did in our 2019 paper for the spatial gradient term, we actually did a type of Monte Carlo simulation of just simulating the types of distributions you would measure with MMS using those statistical uncertainties. So I think we ran it about 100 times and then took the standard deviation of those measurements to see, what type of error we see. So we got on the order of, 10 to 20% of the measurement magnitude in that like region of thermal velocity. But that's for this term. So for the third term, that would take, I think, another type of analysis. The errors would probably, I assume, be worse in this term since there's so many more cadences involved. But you're right, we would need to have like an error plot, on top of this, right?
So
To see the bars.
particularly you have lots of pixels and then this high time resolution. So
Mhm.
how many electrons are there in the typical pixel there?
Oh, like for the counts to actually.
Yeah, yeah,
in
so
each
now
bit.
you're
Right, yeah.
getting into Poisson statistics.
Exactly,
and then it
exactly,
really
right.
becomes-
Yeah, and even just the error propagation for these types of measurements is difficult in itself, but at least the Monte Carlo approach, we used the Poisson statistics, the uncertainty of accounting. You can imagine like, the full 16,000 bins that we measure would go out to like 2 or 3 times the thermal speed here. But so we're probably looking at around 5,000 pixels that have reasonable counts. So we could also plot like the 1 count level and see where the ring kind of starts to fall off. You wouldn't want to trust the statistics below that. So yeah, I think some more detailed analysis, I absolutely agree, would be needed to, to really kind of, maybe back to your question of the physics of, how much do we trust that last row? So that was kind of a first step to saying what we might be able to do, and didn't think we'd be able to do, but, we're starting to be able to do. But,
So Jason, these are all for electrons. Do you have a sense of how this would be for like, if you tried doing it for the ions?
Who cares about the ions?
I like my labs. Yeah, that's on the future work to do list as well. I've done some preliminary checks. I'm especially interested in things like the bow shock, for example, where you have this very, narrow ion beam where a lot of ions are happening in solar wind. And you see that beam hit the shock and it just thermalizes. So you can imagine that gradient, especially the ion Blatov equation would be very much just sitting there to be explored with this as well. Certain limitations, sometimes, the ions will have really just distinct populations that are separate. You might have a core, like a very core ion beam, and then you have like a sort of a halo distribution as well. You should perhaps expect to see these types of quadrupolar features happening within each population, right? If one of them is changing or moving around, then you'd see that separated in the ion Blatov or ion velocity space. That's my guess, but still to be determined. So haven't gotten there yet. Maybe you can help me do that. So, yeah.
Right.
Okay.
I think we're now.
Yeah, I think we're over time here, but thank you all for staying.
Boys,
That's
no
okay, I forgot to
Andrew
mention,
boys.
so it's another Jim Harper story. So he brought one of these little green rattle back into class one day. I don't know if anybody has seen these, I don't know a lot of you have, but, and he just asked us, he said, don't Google it, just try and think about how it works. And, and if you're stuck, research, search and search and search again. And so, yeah, so if you're interested, you can take one of these. They're one of my favorite little physics toys. I did try to understand it for Roy's classical mechanics class. That was my final project. I think I got a B on that paper, but it's very puzzling how this thing works. So you're welcome to take one if you'd like as well. We're good little giveaways.
Can you give me the other one?
Sure. I love this. It's like a fidget spinner for physics nerds.